Um, I hope it's working. Okay, seems like it's on. Okay. Yeah. So, this is A level revision. This stream will be. It's very hard when it's the first paper because obviously you don't know anything that's going to be on it. It's not like say with GCSE where we're on paper 2 now, so I can start to like whittle down topics. So it's quite hard to kind of give good revision. So I think the best bet is really to do the past paper, like I've been doing so far. And that's what we're going to do. So today, this is June 2022, paper 2. So I did June 2018 both papers and 2022 paper 1. So now we're on paper 2. But I will say I will not have enough time to do every question. So what I've done is scanned through the paper, picked out the more interesting questions, right? I'll give a brief commentary on the other questions, but I'm not going to go in depth like the other ones. I'll just quickly tell you how you should approach it and stuff like that. But that's the aim. So just to have a look at go through some of these questions as part of revision, right? Revision resource if it helps anyone out. So yeah, that's what we're gonna do. So I'm gonna just get started on, I guess. Okay, question 1, and I do love these sort of inner modulus questions with a graph. And so we're giving us this graph-wise mod 3 minus 2x, and we need to solve 3 minus 2x modulus is x plus 7. Okay, so the thing with all these modulus equations is you need to sketch them, and actually they're giving us a sketch already. But we need to sketch x plus 7 because this is the same as saying the graph y is 3 minus 2x intersects the other graph y is x plus 7. So we've got the graph of y is 3 minus 2x, now we need to plot this other one, x plus 7. Okay. And the other thing with sketching, it's a good idea to kind of get an idea about the gradients and the y-intercepts of both of them to aid with sketching and see where things are. So mod 3 minus 2x, well, you can rearrange it to well, it's going to take away the modulus. Let's ignore all that, right? Y would be minus 2x plus 3. So that's telling you your gradient is minus 2. And you can see that here, it's going minus 2. And then this side, obviously, that's where the modulus function's kicking in because it is meant to go negative, right? But obviously, when you go negative below the y-axis, it rebounds up instead to preserve the positive number. So then the gradient on this side is 2. So what's going to happen is this line here, the modulus line, is going to be steeper than this line because the gradient of this line is just 1. However, notice the y-intercept is 3 and this one's 7. So actually, if this is going to be 3 and we're going to need to have the y-intercept at 7, and it's going to be a gradient of 1, so it's going to be like y is equal to x. But obviously, it goes for 7 instead. So actually, it's gonna look like this, right? And because the gradient is more shallow, it's gonna be less steep than 3 minus 2x, which is where which is how you can try visualize and plot the line. Okay, so that's the sort of strategies. Plot the lines, consider the gradients and the intercepts to help you locate and determine where the lines cross and stuff like that. And actually, notice there are 2 intersection points as a result, which is here and here. And the strategy really is, well, we have going to have 2 different equations depending. So this side really, this side is where this V shape, the modulus graph, isn't being reflected, right? This left part before it rebounds up at 0 here. It's the same line as this, right? So that means simply 3 minus 2x is x plus 7. That corresponds to that intersection point there. And then we go to solve this, right? So then we add 2x to both sides. You can have 3x is 3 minus 7, which should be minus 4. So x would be minus 4 over 7. 3, sorry. 3. Yep. So that's one solution. Because we're solving for x, we don't need the y coordinate. It's not asking for a coordinate, it's asking for the value of x. That's one point, but there's another intersection, and it's here. But this is where this graph reflects up. So that means you're going to do minus 3 minus 2x, because normally at this point, obviously it'd be negative. But if we negative and negative, it becomes a positive, which is what's happening up here. So we need to flip the signs to be a negative, and 3 minus 2x is x plus 7. And then you can add negative, expand it. So minus 3 plus 2x is x plus 7. So you can take away x to both sides. So you have x equal, and then add 3. You should get x is 10. And those are our two solutions with only two intersections. So really, the main strategy against Sketch, but really with these sort of modulus equations, mostly you're going to just want to consider the case where you just take off the modulus. So simply solve the positive case, 3 minus 2x is x plus 7, and then you do the minus. So then you do 3 minus 3 minus 2x is x plus 7, and you solve both of them. Usually it's how it's going to go. But the reason why you want to sketch the graph is to see specifically what points, where the points of intersection are, to aid you with your solving. But that's a fairly nice one. So that's question 1. Question 2, I'm not going to do fully. I'm just going to give some comments. So curve of equation for y is 4x. That's going to be very similar to e to the x because it's an exponential. And actually, e, remember, it's just a number, 2.71. It's actually a form of a to the x, and you should know the graph of a to the x for any number a. But it's kind of like 4. So really it behaves in the same sort of way. And the intersection of the equals, so therefore if you know the graph e to the x, but e to the x has this sort of shape, right? So then 4 to the x, well, it's going to be the same behavior. So it's what's the only intersection is going to be with the y-axis. But what happens where this occurs when x is 0, right? So when x is 0, 4 to the 0 becomes 1. So the intercept will always be 1. And so it'll still have that shape where the asymptote's at 0. But because it's 4, it'd be a bit steeper. Because I guess it'd look like that, right? In a weird way. But yeah, that's your graph. And then to solve it, 4x is 100. So then you can just take logs. So you can say ln 4x is 100. So then we then use the power, just either the log rule. When you get a power, you can bring it to the front. So x ln 4 equals ln 100, sorry. Take logs of both sides, is ln 100. And then you just divide by ln 4 to get x. And then you round up to decimal places, but I'm not going to go through that there. Okay, question 3 I will look at in more detail. So this is fairly common as well. This sort of a recurrence relation. When you're dividing, this is a recurrence relation, which means with a sequence, you're relating a sequence to the previous term. So here, an is the previous term, and then you use it to create the next one. And then it's recursive, right? It keeps going on and on by resubstituting the previous value in to get the next. That's just what recursive means. But you don't really need to know that for here. You just need to know how this sequence will work. So before we do any of this, we're looking at periodicity or whatever. Let's try. And this is a very good strategy with unfamiliar sequences, right? Try and series as well. just plug in the first few numbers and then see what you get. So we know A1 is 3, so then what would A2 be? Well, it's going to be 8 minus A1 by this rule. But we know A1 is 3, so it's 8 minus 3, which is 5. And so then A3 is going to be 8 minus A2, which is 5. And that'll get you 3. Then A4 would be 8 minus 3, which should be 5. And actually, hopefully you notice at this point, the sequence alternates between the same two terms there, 3 and 5. So we're going to get 3, 5, 3, 5. And you should recognize that when a sequence repeats like this, it is a periodic sequence. It's like a sine graph, right? Repeats every 360. That has a period of 360 degrees. So when when the graph of the sequence, when the graph repeats, that's your I should say as well before we go on to the next bit to show it's periodic. So say it's a periodic sequence as it alternates between 3 and 5. So it's repeated by the same numbers, right? So then for the second part, we need to state the order. So what that means essentially is how many different numbers there are essentially. So obviously we've gone from 3 to 5 and then back to 3. So it's 2 times. So the order is 2 essentially. So how many times do you from the starting point do you get to the next to the next to the same spot, right? So we start at 3. How many terms do we need to get back to 3? It's like with the sine graph, right? We start at 0. We need to take 360 degrees to return to where it was, right? To create the shape again. It's the exact same premise here. So the order or the period of this sequence is 2. Okay. You can see as either how many numbers there are in the periodic sequence, how many times it's alternating, or just how many times you get back to the starting number. Anyway, that's just the order, not to overcomplicate it. Okay. So then part B is asking for this summation here, which again is pretty typical. So 85 between n is 1 and an. Oh god. Okay. So again, like I said previously, if you have an unfamiliar sequence, just consider the first few terms, right? So what this is saying is we're summing an from a1 to a85, right? Which is this number here. So this is the starting point, and then that's your end point, and you're adding every term in between. That's all that's going on here. So a is summing an, so substitute n is 1, n is 2, n is 3, and you're adding all the terms. That's what this little um that's what this fancy symbol means. It just means the sum of. Okay. Anyway, so what is a1? Add a2, add so on, and a85. Well, we know the first term is 3, and then we know a2 was 5, and then a3 would be 3, and then a4 would be 5, because it obviously it just switches like this, and then it goes on, and then we left with a85. Okay, so what the key idea here is now is we need to spot that actually we can well what you do not do is just add it 85 times and do the whole series. You need to pattern spot and realize we can split this up. And actually the best way is actually because we can't you'd recognize we have an even amount of 3 and 5s, but actually this 85 is odd, so you can't just say 85 divided by 2 and then that would be what, 42.5. but then you can't have half a term. So you can't just exactly divide the amount of 3s and 5s by 2. But what you can do is actually instead consider the first 84 terms. So this is the same as saying between n is 184 of an, and then you add the last term on its own. So what I've done now is just have the even amount of terms, which I can divide by 2, and then add on the last odd term. Because what that will allow me to do is actually then divide by 2, because 84 divided by 2 is a nice number. That is 42. So then, and that means there can have to be 42 lots of 3s and 42 lots of 5s, right? Hopefully you can see that. Because there's the same amount of 3s and 5s. So if you divide by 2, then it has to be the same amount. And then I said at the end we have this A5, 85 that I've just that we just add on at the end. So that's all good, but we now need to work out A85 is. Well, if I then notice a bit more, if I look at it a bit more deeply, I notice A1. Oh, sorry, A1, A3, A5 is 3, and A2, A4, A6 is 5, right? Notice that? It goes from 3 to 5 to 3 to 5. That's what's going on here. And actually, I noticed when the n is odd, it's 3. Well, 85 is odd. So actually, A85 will be 3. So we add another 3 on, and then we put all that into the calculator. And that would get you 339. Okay. And yeah, that's really it. It's very typical with these sort of periodic sequence questions to add the terms. And the whole idea is you need a pattern spot that you can split them up because they repeat. So here, and the best strategy is if you have two numbers repeating, if you have say an odd summation, you can then just consider the first even amount of terms. So if I knock one off, 85 goes to 84, which I can split up even nicely in two, right? Because 84 divided by 2 is 42. And then I can add the last term separately. That will allow me to manage it a lot more better. Say if we had 3 terms, for example, say if we had an order of 3, for example. Say if we had 3, 9, 11, and 3, 9, 11, and so on. Say if this term you have to sum to 100, for example, from 1. Well, actually, 100 divided by 3 is, again, not a nice number. It's 33.3. But what I can do is find, if I keep going down by 1, to then get a number that is divisible by 3 exactly. Right, it's 99, isn't it? So I can say from n is 199, add the 100th term. Um, uh, and then 99 is divisible by 3 exactly, so it's going to be 33, lots of 3, add 9, add 11. 33 lots of 3, 33 lots of 9, 33 lots of 11. And the 100th term, well, we recognize, then you can recognize, well, what's the 99th term? Well, it's going to be 11. Because I notice this is in multiples of 3. So 11's in the 3, 6, 9, and 99's a multiple of 3. So then if A99 is 11, then the next term will be 3. So 100 would be 3. So then if I put that into the calculator, I can then work out the series of this. That's just an example though, but that's a really good strategy if you're ever struggling about how exactly I can you might be able to spot it quite easily, but if you are a bit struggling how to split up the series, right? That's a good way of doing it by doing it like that to split up the summation so you can divide stuff. Okay. Okay. Hang on, let me just check I'm right so far. So question 1 was right. Question 2 was fine. 339 was it? Was that what I got? Yeah, cool. Okay, question 4 again. I'm not going to go over this, but I'll give a brief commentary on it. So this is proof by first principles, which you should be very familiar with by now. Essentially, just need to say, well, by first principles. This is in the formula book actually. It's over here somewhere. It's here. Oh no, hang on. Not there. It's in the differentiation section. There we are. First principles. You need to basically do this limit here. So if I copy that in, the first principles would be f dash of x would be the limit as h tends to 0 of f of x plus h minus f of x over h. I've just stated that, right? And then really all I do from here is substitute x plus h into this. So if y is f of x, then I substitute x plus h in place of x. So that would be lim as h tends to 0 of 2 of x plus h squared, because f of x would be 2x squared, right? So replace x plus h with x squared. You get that squared, and then minus f of x is minus 2x squared over h. And then the idea is you expand this bracket out, and then you should be left with terms in terms of h. Everything eventually will be in terms of h. So you'd have like if I roughly do it, you'd have like you'd have 2x squared, and then you had I think 4xh, and then h squared. Then you'd be able to divide by h, and then if you substitute h is 0, then eventually this will be all down to 4x, and that will be your derivative, okay? But I'm not going to go over that there. Hopefully you should be very familiar. It's a very, very standard proof, okay? But we'll be doing an example of that tomorrow, actually. First principles for the revision session tomorrow. But anyway, I'll leave it there. So question 5, I'm going to go over this as well, because it's quite an interesting question. So we are given the table below for this function here, y is log 3 of 2x. And the values of y are given to 2 decimal places as appropriate. So they're giving us some data, so it's very clearly going to be a trapezium rule question, right? Essentially, for part A, we need to use the trapezium rule to evaluate this, right, between 9 and 3. So the trapezium rule, again, is in your formula book. It's here, right? It's really long-winded sort of thing. I'm going to write it all down, actually. Oh, wrong one. So the if we set it now, God's sake. So the integral, what was it? H over 2 of y0 add yn add 2 lots of y1 add y2 add add y to the n plus 1, where h is b minus a over n. Well, obviously, and b over a, so this is the integral of b to a of f of x dx. That's what's written in the formula book, essentially. So you don't have to memorize that bit, but you do need to know how to use it. So what we need to work out are these values. We need to find what h is going to be, and n, I guess, but what h is. So b minus a is essentially your limits. So we have 9 of 3 of log 3 of 2x dx. So h is going to be b minus a, which is 9 minus 3 over n. Now, this is where you need to be very, very careful because n corresponds to the strips we have. So if you imagine, there's two ways of kind of learning this really. If you then consider this sort of general curve, the strips we have, essentially, we are forming trapeziums at each of these points, right? X is 3, then X is 4.5, and then X would be 6, X would be 7.5, and X would be 9, right? So there are 5 data points, right? However, look, there's only 1, 2, 3, 4 strips, or trapeziums, right? Strips or trapeziums, whatever you want to call them. So actually n would be 4, not 5, because there's only 4 trapeziums, right? Despite 5 data points we pick. So n would be 4. However, another way, if you don't want to, I don't know, if you don't want to be too geometric, is look at this formula. So what this is saying is y0 is the initial value, right? Which is 1.663. And we know that the final point is so we start at y0 essentially. Y0 is the initial point. So then that would mean that would be y1, that would be y2, that would be y3, and then that would be y4. Now n is the last point, which is the end point 2.63. That means y4 is yn. So that means then if you just compare, n is 4. Okay. So you can use the formula to guide you in that way as well. So if you call the first data y0, then you can kind of work out that the last point would be the 4th point, right? If this is like the 0th point, then that's the first, and that's the second, and then that's the third, and then finally the 4th one, that's your end number there. So that therefore means n is 4. The multiple ways, I've just covered 2 ways you can kind of work that out. So then I found h. And so this will simplify to 6 over 4, which would be 3 over 2. So I found h now, and I know what n is. So n is 4. I can then do stuff with this formula. So the integral becomes, by using this formula, h over 2. So it's 3 over 2 over 2. And then y0. So we need the y values, right, of the points. So we need to look at the y bit. So 1.63 is the first one. And then yn, the last point, y4, the end point is 2.63. Okay. So 1.63, let me make that a bit clearer. 1.63, add 2.63. And then we're going to have 2 lots of everything else. Right. So that's 2 lots of, what are the other points then? How to scroll up. 2, add 2.26, add, what was the other one? 2.46, okay. And then we just evaluate it, put that into the calculator, right? So 3 over 2 over 2, that would be 3 over 4, right? Yeah, 3/4 of 1.63, add 2.63, add 2 lots of 2, 2.26, add 2.46. Oh, no. And that whole thing goes to 17.7. So then that will go, if times that by 3 over 4, you should get 13.275. Does it ask for any particular way of writing it? Find an decimal. Okay, so you just leave it as a decimal. That should be the right answer, hopefully. 13.3 or yeah, that's the right answer. Cool. So that's basically just using the trapezium rule. You don't even need to learn the formula, but you do need to know how to use it. I mean, but even I haven't used this in absolutely ages, and I've still worked it out. The formula, you can work with it really, especially if you know what you're doing. And again, like you can use if you're struggling to find what n is, it tells you what h is here as well. So it should know b minus a is the endpoints of the integral, and then the n you can use the formula to guide you. So you know that what it has to start at y0. That means it has to be the first point. So y0 is obviously going to be this. So then you can get going up to find the last point, and that's the first one, then the second one, the third one. That's with the fourth one. So you have to start from 0, not 1, essentially. You count your way up. That'll tell you your n. That's how many strips you have. And then you found n, you can just use the formula essentially. Plug the values in, and yeah, I'm gonna leave it there then. Scenario part B. Um, Then it says to use your answer to part A to estimate some related integrals. So the first one is the integral between 9 and 3, was it? 9 and 3 of log 3 2x to the 10, was it? Okay, so what you need to do is compare it with the original. So I'm going to write here the original integral was 9 and 3 of log 3 to the 2x dx. Right? So basically, what we need to do here is pretty much use log rules, right, to be able to use this to get to look like this expression here. Okay, well, the first bit I immediately notice that I can use the power rule, right? That I just talked about earlier. So if you have a log of a to the n, that's the same as n log a. Okay, so I can just bring the power out. That's what I've got here. I've got a power of 10, so I can bring that out to say 10 log 3 of 2x dx. And now I can use it because now I can just multiply the uh, the integral we had by 10. Right, we can bring the 10 out afterwards, outside the integral. So that's going to be 10 times 13.2675. That's my answer. And then I'm going to get 132.75. Or if you want it that as a fraction, that is 3.531 over 4. Okay, it doesn't matter how you write it. Okay, so that's a fairly simple one. Now we need to deal with this integral, which is log 93 log 318x. Okay, log 3 of 18x dx. Okay. Okay, well, this one, again, I'm going to rewrite the original here to make it clearer, side by side. That's 9 and 3 of log 3 of 9x. No, it wasn't, no, 2x, wasn't it? Sorry. 2x dx. Yes. But we have 18. But I want to use the original, so I'm going to need to make it look like this. So let's try perhaps log 3. Let's try and make 2x from this. Well, I know 2x goes to 2x times 9, right? Because that would get me 18x. And the reason why I want to times is I have the back of my mind that this. So with this sort of question, you need to bear the log rules in mind. So you have this log rule, which is log of a to the n is n log a. But also the other one is log of ab is log a plus log b. So those are the two log rules you need to have at the back of your mind. So here I want to create a times, right? I need to have some sort of product if I can do anything. I can't raise it to a power. I can't really do that. So the only option I have is to make some sort of product and use a 2x. So 2x times something. And actually, then I can say that's 9 and 3 of log 3 of 2x add log 3 of 9, because then I'll split up the logs. Well, actually, I'm good because I'm going to need more writing. Obviously, this first integral is exactly log 3 of 2x. That is the what was it? What did we get in part A? That was 13.275. But then we need to deal with this bit. But this bit's fine because it's a constant, isn't it? Really? It's a constant, so we can integrate that very easily. So then I could say, well, if I call this bit k, then that's going to just be kx between 9 and 3, right? Yes. I'm just trying to make it clearer. So then 9 3 of log 3 9x, 9, sorry, dx. Then that will be 13.275. Then that'd be x log 3 9. But I think I notice that 3 and 9, there's a link between them, right? Because I noticed we're going to need to simplify this properly because it, it's not going to be a nasty log in the answer, probably. So I notice there's a link between 3 and 9 because I recognise that this is log of 3. Well, no, I noticed log 3 of 9 isn't 9 3 squared. And then I can bring the power out again to 2 log 3 3. But log 3 of 3 is just 1, right? Because you can put that into the calculator. In fact, I think you could put this in. You could then put this into the calculator, right? Actually, if you weren't comfortable with index laws, especially with like a different base. Usually, you use like base e, right, or base 10. But if you wanted to, you could actually put this into the calculator. So log 3 of 9 will get you 2. And that's easy to see because this will become 2 log 3 of 3, which should be 1 times 2, which is 2. So hopefully you can see that, right? Because also bear in mind, log 3 of 3, that's the same as saying what number that's 3 to the something gets us 3. Well, that something is 1. So, yeah. But anyway, that might be a bit confusing, but if you wanted to, you could put that into, because it's a definite number, you could put that into the calculator, right? So then that's the integral of 2 dx between 9 and 3. So that's 2 lots of log 3 3. Because 9 is 3 squared, then I move the 2 to the front. And then I have log 3 3, which goes to 1. So then 2 times, well, 1 is 2. And then this I can integrate. I know how to integrate a constant. So that's 13.275 plus 2x between 9 and 3. So that's going to be 13.275. Add 2 lots of 9 minus 2 lots of 3, right? Because I substitute the upper limit and take away the lower limit. Put all that into the calculator, I get the answer. Minus 10.725. Oh, no, don't, sorry. God damn it, signs. No, you get positive 25.275, and that should be your answer. Okay, so yeah, they do look asking like you making use log laws as well. So you need to be prepared to use the log rules, right? And it should be hopefully fairly obvious when you use it, right? because obviously this is to do with logs, right? I can notice I'm changing the log up, so I'm going to need to use the log rule somewhere, okay? And again, if you write down the two log rules here, then hopefully that should help you realise what you're going to use, what you need to do, right? Okay. So question six, I'm going to go over briefly, because I like to go over the more tricky one, right? Because that's a fairly tricky one, I feel like. So it's good I went over that, but this one isn't too bad. So we have a curve, and they're given the equation here. And what it's asking us to do is this point P is a local maximum, so that means it has to be a stationary point. So yeah, to find the x coordinate, that's what we're going to do. So the x coordinate corresponds to dy by dx equals 0. So if I differentiate this, you would you would get 8 cos times a half. So that would mean 4 cos of half x minus 3. That will differentiate to minus 3, and 9 would go away because it's constant. And you have to set that to 0. You then need to essentially solve the equation. Cos of a half x would be 3 over 4. And yeah, and that would be the first positive solution. So when you arc cos it, that would be the x coordinate, okay? So that's how you solve that. Because obviously that's the first. Oh, actually, no. No, if you look at the graph, there's one turning point there. Could you see there's dip, it's going from increasing to decreasing. There'll be a turning point there, a turning point there, and then a turning point there. So you'd want the third positive solution, right? Actually, I'll go over this point briefly. So a half x then would be cos inverse cos of 3 over 4. So half x would be 0.27227. Then if you use the cos graph to find the other solutions, 0.72 when 3 over 4, that would be about there, right? So then the next solution would be there. Hang on, let me draw a more better cos graph. There we go, something like that. So 3 over 4 would be about there. Oh, got to say. It would be about there. So then the x coordinate wasn't, no, well, twice of that. But then to get the other solution, then you'd, I notice that, if this is 2 pi, the distance between here and 2 pi is the same as between 0 and this solution here, 0.72. So then to get this solution here, so that's 2 pi. Well, the distance is 0.72 because this is a 0, so it's 0.72. What I'm going to do is do 2 pi, take away 0.72, and that'll get you the next solution here. So the next one will be 5.5604. And so then the next solution, and then you add 2 pi, so you add 2 pi to the next one. So 0. And by the way, if you are but unsure with this, how you worked out the next solution, you can just put that into the calculator. So cos of 5.5604 gets me 3 over 4. So it gets me the number. So that is right. Okay, the solution there. So the next solution, you add 2 pi to each of them. So 0.7227 was it? I can't even read my own handwriting. 0.227, yes. So then you add 2 pi onto that. Then you get 7 0.0059. I know, and that's our third solution, right? That should be P. But then that's a half x. So x would be 2 lots of 7.0059. Because remember, we want the third positive turning point. So we want the third positive solution here. So then that would be 14.0. 3 significant figures. Oh god, it'd be like 01, would it? Or would it 14.0? 14.0. Okay. Okay. Yeah, but that's how you do that part of the question. It's a fairly tricky one because I think some people would probably just take the first value and then that'd be its coordinate. But you need to use the graph to realise it's the third turning point because we already have 2 more before it. Okay, so you want the third solution. Okay. Okay, but that was that. The rest of it should be fairly straightforward. So explain what alpha must be in the interval. So we're looking for the roots now. So that is when f of x is 0. So you'd 8 sine of a half x minus 3x plus 9 is 0. If you call that, again, if you call that f of x, like we just did, then if it has a root between, well, it tells you here, f of 4 is greater than 0 and f of 5 is less than 0. So a root must be in the interval. I did say I wasn't going to go over it, but 4, 5. And the key point as well is because there's a change in sign and the function is continuous. So here, that means you're not taking the pen off the page, right? There's no gaps, no holes, no anything. But this, for example, would be a continuity because there's a gap. So we have to take a pen off the page, right? So this is continuous though. So because it's continuous and there's a change in sign, so it's going from the positive to the negative axis. The only way it can do that is by crossing through the axis, so it has to be a root. However, if it was discontinuous, say we had a graph that looked like this, so it tended towards the asymptote of 1, say y was 1, then it could look like this. But actually, if we took the sign change here and then here, you're going from positive to negative. But so if you just use the sign change, you'd think there's a root. But actually, it's not crossing through the axis. But because there's a discontinuity, there isn't a root because we just jump in the graph right to another part. So that is why it's important. It also has to be continuous in that interval, right? So you can see the graph's continuous. So because of those 2 bits here, there's a sign change and f of x is continuous. So the root must be in the interval because the only way it can go from positive to negative in that case is if it crosses through the axis. So i.e. so it's a root. Okay. And then part C. So then if you use the Newton-Raphson, so you should know the Newton-Raphson's in the formula book actually, but I believe it's xn plus 1 is xn minus f of xn over f dash of xn. Well, we found f dash in part A. So if you just substitute f dash of x, then you can substitute all that into the formula and f of x, and then you substitute x0 is 5, and then you find x1. And then you round up to 3 significant figures. Okay, that shouldn't be too bad, hopefully. Okay, I'm going to move on though. Question 7. Again, I'm not going to go too much into this, but again, I'll bring that up. Actually, it's going to skip it, isn't it? But the binomial expansion of 1 plus x to the n, where n is any and a fractional or a negative indice, that that is in the formula book. I think it's 1 plus nx plus n of n minus 1 over 2 factorial xn, x squared, sorry, plus dot dot dot, and then plus, what is it, n of, I don't know what the final term is, but it goes like that, I believe. In fact, I'm going to double check I'm right here. And I'll show you where it is as well. It's here. There we are, this part. They don't really tend to ask this the normal binomial in the AS version in the year two paper. Normally you I expect to use this one. So here you see n minus 1 over 2 x squared, and then it goes on. And that's the general pattern. Okay. So you just need to substitute that into the formula, but we need to basically the main difficulty with this is you need to convert the square root into this sort of bracket. Well, you just use third rules here. So 4 minus 9x is going to be 4 minus 9x to the half, but this constant 4 has to be a 1. So what you can say is we can factor a 4 and then say 1 minus 9 over 4x all over a half. And then I can bring the 4 out. Because now, again, if you know the power law, a to the mn, that's a to the mn, so you times the powers. Well, 4 to the 1 is kind of 4 to the 1 times the half, so it's going to be 4 to the half times by 1 minus 9 over 4x to the half. And now this is in this form here, but x, or I should say x here, is going to be minus 9 over 4x. That is what you're substituting in x here, and n would be a half. And then you just substitute that to then get the, let me put my charger in. And then you substitute that to get the first, how many terms did it want? The first 4 terms. So that's going to be the constant term 1, then that's going to be the second term, the third term, but then you're going to need x cubed, which if you follow the pattern, n of n minus 1 and n minus 2 of 3 factorial x cubed. That'll be your fourth term. Okay. So you go up to x cubed, and then you just substitute that n and x into the formula, and then simplify. Then it says for part B. Then it's commented asking to say if you use the expansion to approximate something. Here it's root 3. Is it an underestimate or an overestimate? Well, actually, if you were to carry out the series, if you did it in part A, you would actually get a negative. So it'd be 1 minus some lots of x minus some other lots of x squared minus some other lots of x cubed. So what's happening is each time you add a term on, it's more negative. So actually, if you think about the true value, it's infinitely many lots of xn's, right? So actually, you keep adding, like you're subtracting more and more terms, you get a more negative answer. So if we were only cutting off some of it, that means our answer is going to be more positive. So it's going to be an overestimate. Okay. If we're only using the first 4 terms, because if we had more terms, it would be more negative. So it would decrease. So that means cutting off the terms makes it an overestimate. Okay. But yeah, that's just a general guide for that question. I'm not going to go over it too much, but yeah. Okay, this one again, I'm not going to do it fully. Just give a brief explanation. So, we have figure 3 here. So it's an area one. It's a fairly simple one, really. So we need to find the area of the curve. So again, it's going to be between the lower and the upper limit. Right, it's where the curve crosses the x-axis. But we are given the curve, and actually, if y is 0, that means the numerator has to be 0. So x minus 2, x minus 4 has to be 0. Now, not 4 root x, because imagine if you had x minus 2, x minus 4 over 4 root x, for example. If you have that equal to 0, you might be tempted to cross multiply, and you can. But obviously then 4 root x times 0 is still 0. So then you're just left with x minus 2x minus 4 is 0. So it's just the numerator. And very simply, that means it's going to be the roots of 2 and 4. So it can be integrating between 2 and 4. And we're going to integrate this function. And it looks a bit nasty, but really, it's AS integration. It's just indices. Because to x minus 2, x minus 4 over root x, if we first expand 4 root x, sorry, if we first expand it, we get x squared minus 6x to the 8, right? Over 4 root x. Then I can I can split the root x up into a half. I can use index laws. 4x to the half. Then because this is a fraction, we can just split it up each term wise. So x squared over 4x to the half minus 6 over 6x over 4x to the half plus 8 over 4x to the half. Hopefully you see that, because we're if we have the same common denominator, we can split up the adding and subtracting, right? And then I can use power laws, so that's going to be x squared. So that's going to be x a quarter x, and then when we use the power law, a to the m over a to the n is a to the m minus n. But that's from G to 0. I hope you should be fairly comfortable with that. I subtract the powers. So 2 minus a half is 3 over 2. Minus 6 over 4 would be 3 over 2 of x minus x to the half of x to the half. 1 minus a half is a half. And then 8 over 4, which is 2, x to the minus a half. Right? And then that is what I'm integrating. A fourth of x to the 3 over 2 minus 3 over 2 x to the half plus 2x to the minus a half dx. Now that should be fairly manageable, right? And the last comment, once you do all that integration, you're going to get a negative answer because the area of the region is strictly below the y-axis. So you get negative y values, so you get a negative integral. However, because it's an area, you're going to need to flip the sign. So you either do a minus, or you could just do a modulus outside. So you flip the negative to be a positive because area is positive. Okay. And then you get this form in the end. But yeah, I'm not going to go too much further into that. Hopefully, if I just step the question, explain where it all comes from, hopefully the doing it after from that should be fairly straightforward. Okay, this one I am going to do in more detail. Okay, so we are given, let me zoom in now. We are given this little it's a modeling with trig. So we're given this curve here, which represents the basically the height of the Ferris wheel above ground. And it's given by this function. And actually, what we need to do is find a, b, and alpha. And it's fairly typical. We are given some data, some information, some conditions, and then we need to convert this into maths to then find a, b, and alpha. And that's what we're going to do. So, I guess we're going to start going one by one, right? So, part A, I'm going to use the first bit of information first. That's going to mean, well, maximum height above the ground is 50. So that means when h max, so the maximum value is 50. Okay, so that means the max of mod a sine of bt plus alpha degrees is 50. Okay, but how would I find the maximum value? Well, you're going to need to know that sine of anything, of any angle, is between -1 and 1. You can see that by the graph, okay? It goes between 1 and -1. So the maximum of that is going to be 1. So therefore that means mod A is equal to 50. So that means actually A could be plus or minus 50. But I'm going to take a 50 because, and I'll explain why. Actually, the mark scheme, by the way, you can have either, but I'm going to explain actually what is the better one. Because, notice, this is applying the modulus. But if I get rid of the modulus, this is just a sine of bt plus alpha, no? And it's just a normal sine curve. But actually, again, look at this sine curve I just sketched. This represents obviously the first little hump, right? From 0 to pi. Is that not just the original sine curve without a modulus in? Because remember, if we have a modulus of a graph, like we did in question 1, the negative gets rebounded up. But here at this initial, the initial from 0 to pi, it's not being reflected up. It's the original curve. So actually, the modulus, we can get rid of it, and it'd be the exact same function. So actually, this is almost the same as saying just a sine beta is 50. So a would be 50. And I guess you could say as original curve a sine bt plus alpha is identical to the modulus for those sort of values, right? For the starting sort of values. Now, actually, you do notice there's a little rebound up here. So actually, that's not the end of it, but there's a little rebound here, and that is why it allows you to have plus or minus a. Because actually, there's this little bit here it rebounds up, but most of it is the same. So we just take the positive. But as I said, the mark scheme allows either or, because technically you can have either or. But I think that's the most sensible solution. So if that's the first condition, A is 50, so reduce the maximum. Then it says the passenger is 1 meter above the ground and the wheel starts turning. So that's T0, then the height is 1. So actually we can just substitute that in. So therefore, mod, and as I say, you can probably take away the modular sign, but I'm going to say mod 50 sine of bt. Now T0, so that'll just go to 0. So it'd be add alpha. And that's equal to, what was it, 1? The height was 1, right? So, and then I said h is 1, t0. So we get this. Well, actually, then, sign out, again, like I said, I'm going to get rid of the modular signs. Because it's the same graph. So, sine of alpha be 1 over 50. Therefore, alpha is going to be inverse sine of 1 over 50. Put that into the calculator in degrees, remember, because this is in degrees, alpha degrees. You get this number here. Hang on. No, I'm in radians still. That's why it's such a weird number. No, degrees. There we go. Sine inverse 1 over 50 is, there we go, 1.14599. Bloody fly. 1.14599. But do we need to leave that exactly somehow, or can we round it? Let me have a look. I think it's rounding, right? Alpha to 3 significant figures, I reckon. So we could round that then. So to 3 sig figs, that's 1.15, right? To 3 sig figs. Okay, now we just need to find p, but we're given another piece of information. This bit. The wheel take 720 seconds to complete 1 revolution. I guess there are many ways you can interpret this. I guess, well, if it's completed one revolution, it's returned back to this point, and we know at the start h is 1, right? So you could say t is 270, and the 720, h is 1, I guess. But I'll tell you another way you can look at it. This might not work out the way I think it will, which is fine because I've got another way. But let me just play around with it. So h is 1, t 720, because also after 720 it repeats back. When it repeats a cycle, what did it say? Revolution. That just means it returns back. So like a sine curve, I guess. Well, I mean it's a bit different, but it's returning back to its point at the start. Okay. So h is 1, t 720. So I guess that would mean 50 sine of 720b plus alpha is 1. Now you could solve b. The problem is it needs an exact value of b, and I think because alpha is this really awkward number, if I was to plug alpha in and I get this weird number, I'd probably get a weird number and have to do the trying to think. I think you could solve it like this, but I don't think it'd be very nice. I think they said exact value to avoid you having to solve this. I'm just gonna see. I'll tell you what, I'm gonna leave it there. I might come back to it. I don't know. But another way of looking at this is, well, we know initially it says it as a revolution, right? And again, everything about sine, a revolution is essentially it's done like a hoop, right? So it's gone back to where it was, and you can see that here. It's returned to where it was, and then it repeats the same shape. Okay, and that's in 720 seconds. We can actually compare that to the sine graph. Does this not correspond to a pi degrees, like I just said with the sine graph? So it's kind of like the sine graph. It's again, it's every 180, right? It's pi, 180 degrees. So it returns back. Well, it's supposed to be every 180, right? That's when it returns back. Because notice this is a 0. This basically corresponds to the first hump of a sine graph. Because remember, that's what this is doing. So one revolution should be equivalent to 180. But it's 720. So how have I gone from 180 to 720? Well, I would have to double times by 4, which means I have to stretch the x coordinates by 4. But if I want to times the x coordinates by 4, I have to do a quarter of x, right? Is that not what's going? Oh, a t, I guess in this case. So b of t would be a quarter. So b would be a quarter, right? But another way of doing it is noticing this 180. So if I said this, this is equal to 1. This is when it returns back to the starting position. So this is 50 sine of alpha, right? Because that's when it. Because remember, initially when t is 0, h is also 1, so we can equate them together. And actually, 720 plus beta plus alpha, that's the next cycle. That's the next revolution, right? So this is at the start, and then this is after done at a revolution. Now, as I just discussed, the graph, again, like a sine graph, the graph that we have for h and t corresponds to the hump between 0 and pi or 180 of a sine graph. So that means actually we need to have added 180 to get from the first point to the next, to get to the next revolution. So 720 plus beta plus alpha has to add 180 on to then get alpha. Oh no, sorry, no, that's wrong. Plus alpha is alpha plus 180, right? Because what that's saying is I forgot to say. There we are. Starting to bug out. 180. So our starting value, and then as we said, the revolution is at the next 180. Well, if I add the starting angle and then add 180, I'm going to get the next angle, aren't I? Because again, it's a cycle every 180. Again, I'm going to reiterate that's because that the first bit of the sine graph, it's really playing up now. It's getting on my nerves. Uh, the first part of the sine graph corresponds to the first hump, right? Obviously, it's shifted by 1, but all I've done there is essentially, again, shift the sine graph up by some amount, you know. But the fact is, it's still going to be a hump at 180 degrees next. Now, actually, a revolution of a sine graph, I should be more precise here, is going to be 360 because that's when the revolution is 60 because that's when the shape repeats itself. But here, because it's a modulus sine graph would be like this, but then it would be another exact hump because obviously, if it's meant to be negative, it would reflect up. But then the revolution of a modular sine graph is going to be 180 because it's the same shape, right? So instead of 360, now 180. That's exactly the same reason in here. The next revolution has to be 180 of the starting angle, which means if we have our starting angle, like we've done here, and then add 180, that will get the next revolution, which is this, right? We're told when t is this angle here, that's the next revolution. So if you add 180, you get b. Now we can solve for b. So the alphas cancel. So I'm going to get b. B is 180 over 720, which is again a quarter. So there's two ways we're looking at it, really. Again, you might be able to solve this as well. This equal to 1, but I'm not too sure. But that's the exact value, right? So either you can look at it that way and say, well, 180, so we have to add 180 to the starting angle to get the next because it's the hump of technically a modular sine, but it corresponds to the first hump. So that's how long the revolution should be along, the next 180. Or you can actually reason in terms of graph transformations because kind of what I was getting at to before here. What is this really doing? This bit of information here. Well, we have the sine graph, then sine of bt is gonna squash the x coordinates, right? It's gonna divide the x coordinates by b. But if we divide by a quarter, that's the same as times it by 4, which is what we're doing because it has to be 180, but actually it's told us the T720 instead. So we need to get from 180 to 720, we times by 4, so we need to divide by 4 inside the bracket. Because remember, with transformations, what you do inside the bracket, you do the opposite with x or t. So this means you're times in x or t's by 4. which means you're timesing the t coordinates by 4. So 180 times 4 gets your 720, which they told us. So you need to stretch. You need to squash it essentially with this quarter here. But then this alpha here, so that's b. So b is telling you how much you essentially times or divide the x coordinate, the t coordinates. But then plus alpha, you essentially just shifting it right or left. That's not actually changing the scale, the squashing the scale, right? So if we shifted this by 90, well, it's still going to be a revolution 180, right? It doesn't matter how much you shift it left or right. It's still going to be the same revolution. So the alpha's not going to affect it. And A, that's just doubling your y coordinate. But again, if you times the y coordinate, that's still not going to affect your revolution. So for example, say that's our original graph, model sine x, right? Model sine x plus A. Again, you're just shifting it right or left. So it's going to be, say, here. But it's still going to be 180 along, no matter how long we shift it. Same with A. If I then stretch that up, it's still going to be 180 along. It's not affecting the actual the distance of each hoop, right? This little jump, this hill thing. The only thing that affects the hoop, the hill distance of each curve is our b value, because bt is telling you how much you're stretching the x coordinates in. So if we have b as a quarter, you're actually dividing by a quarter. So you times it by 4, the x coordinates. So actually that would mean you kind of then you'd stretch it like that, which is what's going on here. 180 is turning to 720. So that's that. That's probably really, really confusing, but it's a very hard question. But I'm just giving multiple ways of potentially explaining it. I don't know. Maybe neither of them are helpful. But I don't know if one of them helps you understand that. But yeah, that's the whole idea, right? So now we've found an a, b, and alpha value. It said find a complete equation. You need to be careful it says that, because you then need to fill in and restate the equation. So that means h is going to be mod of 50 sine of a quarter t plus 1.115, right? 1.15 degrees. That was alpha. So yeah, a complete equation is essentially, just to say, you're finding all missing values, right? So that's your complete equation. So you need to restate the equation with all the values filled in. Anyway, oh my god, what a question. Part B. Um, Explain why an equation of the form of this plus d is a more appropriate model. So with this sort of question, this part, you need to recognise what we changed. And all we did was add d. So then you're going to need to think about your graph transformations again. So remember our curve looked like this. So if I get rid of this, we add in d. And d is a positive constant, so it's going to shift up by d units. So it's going to look like this, right? That's what the curve's going to look like. Now, why is that important? Why are we shifting up? That means we want to move every coordinate up. So what's the minimum value that gets shifted? It's this, right? It's when it hits the floor, really, 0. So actually, it's telling you that the height is 0, so we need to shift it up. That's because we're moving everything up. So why is that important? Well, think about it in the context like I just said. When it's 0, the height is 0, so it's on ground level. I mean, is this Ferris wheel? Is it meant to hit the ground? It's going to crash and everything, isn't it? That's not what we want at all. So we're going to need to we're going to have to shift the curve up to compensate for the fact it's always above ground level. So it's a more appropriate model. It's because because it shifts up the height, because that's what it's doing. You shift it up by d units, such that it does not hit the ground, such that the wheel does not reach the ground. So when h is 0, right? And that's essentially what you got to get out, is that it won't scrape or hit the ground anymore, which is not what you want a Ferris wheel to do, right? You want it to just be above ground level. Anyway, so that's that question. Not quite a nasty question that is. But we're on this one then. Question 10. They love asking function questions like these, so again, you do need to be quite prepared for it. But let's go over it then. So question 10. We have a function f defined by this. We first need to find f inverse of 3 over 2. Now, there's two ways doing it. If you're more comfortable, you could realise this is saying, well, f inverse of x, that's saying almost like the y value, right? So what x value, so this is equal to x. What x value gives the y value 3 over 2, because that's inverse of a function. In the inverse of a function, remember, x, y's switch roles. So our input is almost our y value for f of x. So if this is equal to y, it's almost not saying 3 over 2, and we need to find the x value that gives this y value our input. So you could be solving essentially the equation 8x plus 5 plus over 2x plus 3 is equal to 3 over 2, and do it that way. However, I think the most comfortable way, I imagine for a lot of people, if you don't well, you should recognise it actually. That's the whole role of an inverse function. But if you're not comfortable making that link, just find the general inverse, right? Which you should be quite familiar with even at GCSE. So inverse of x. So the strategy again is going to be y is 8x plus 5 over 2x plus 3. And then, like I said, the roles switch around. So now the x you have to rearrange the x in terms of y. So then you switch the roles around, and then that'd be your inverse. Okay, so now we rearrange to get x on its own. How are we going to do that? Well, the best step is to get rid of the fraction. So you can have y of 2x plus 3 is 8x plus 5. And then I'm going to get all the x's on one side. So I'm going to say 2xy minus 8x is 5 minus 3y. And then I'm going to factorize x. Say 2y minus 8 is 5 minus 3y. Therefore, x is 5 minus 3y over 2y minus 8. Therefore, your inverse, then substitute that in. It's going to be 5 minus 3x over 22x. That's 2x, not 24. 2y, sorry, that was y. 2x minus 8. And that's your inverse. So then you're essentially saying, you just plug in f inverse 3 over 2. So it's going to be 5 minus 3 of 3 over 2 over 2 of 3 over 2 minus 8. And then that will be, plug that into the calculator. And you get minus a tenth, apparently. Let me double check. I haven't checked my answers in a while. Let me check the last one. Just make sure I'm not saying anything wrong. Although it's alright. I'm saying the right stuff. Just I don't want to make. If I said anything, if I made a silly mistake, you know what I mean. Yeah. So that was all right, and that's right as well. Cool. Okay, let's have a look at part B then. So there's two ways. If you instead realise this, you'll then get eventually x is minus a tenth if you solve that equation. It doesn't matter though, but you can do it both ways. Then part B says, show that f of x is a plus b over this. So with this sort of thing, you need to realise what's going on. Well, really, the numerator has turned into a constant. How have they done that? Well, you should notice actually, that the degree of the numerator is at least the degree of the denominator. When that happens, you need to do long algebraic long division. Okay. To then get so then you have a constant over the denominator, right? And that's how it works. So that's the quotient, and that's the remainder, right? Oh God. So that's what we're gonna do. I think alternatively, what you could do was just say a of 2x plus 3 plus b over 2x plus 3. Then that would be 2ax plus 3a plus b over 2x plus 3. And then compare that to 8x plus 5 over 2x plus 3. Then you can compare coefficients to say 2a is 8, so a is 4. And then 3a plus b is 5. But therefore b is 5 minus 3 of 4, which would be 5 minus 12, which would be minus 7. So you can do it that way, kind of like partial fractions. But I'm going to do it with long division, right? So, what have we got here? So, what's our function? So, 8x plus 5 over 2x plus 3. Did I copy that right? I did. So now, I'm going to do algebraic division. So the denominator has to be outside the little bus stop here. 8x plus 5. Then I need to think of a number that times, so the 2x becomes an 8x. So it's going to be 4, right? So then 4, and then I need to times by this to then get 8x add 12. And then I'm going to minus it, right? So minus both sides and both terms, sorry. So 8x minus 8x is 0x. So I can get rid of that, really. And then 5 minus 12 is minus 7. So actually then this becomes, by this, 4 with our quotient, and then the remainder of minus 7 over the divisor, so 7x plus 3. Isn't that our value of a and b that we just found by comparing? And we did that a bit quicker. Yeah, a is 4 and b is minus 7. Which is what we've got here. Cool. So again, I gave you 2 ways for that, actually. Being very generous here. Anyway, so then we did that. Then we're given another function g, and it says for c, state the range of g inverse of 1. Well, that's where you need to remember the link between inverse and the normal function. And again, it goes back to this key idea that the roles of x and y switch. So what that means is the range of g inverse is going to be the domain of the original function g, and it goes vice versa. So the range of g of x will be the domain of the inverse, because of because the domain, remember, is corresponding to the values of x, right? And the range of g, like I said, it's going to be like the x, right? Because the x is kind of like the range, the output of the inverse. It depends how you want to learn it, but that's essentially it. But we're given a domain. It's right here. It's 0x and 4. So the domain is 0x and 4, so it's the same sort of way. So the range is between 0 and 4, but then it's going to be g inverse of x, right? Not x, but right, because it's the range, it's basically almost like y g inverse of x. So it's a range of values you get of the function, which is just g inverse of 1. Okay. So you make sure you put g inverse of x, not just x or anything like that. And don't put y either. Because obviously it's a bit different with an inverse function. Anyway, so that's for 1 mark, and you kind of should realise if it's only 1 mark, you don't really need to do much there. And it says state. So it's kind of like just look at the information you're given and just write something down based on that, which is what we've done here. So you've looked at the domain and then you've copied it essentially. Okay, so then part D says find the range of FG inverse. So you need to realise that it's a composite function. So it's f of G inverse of x. Not the even at GC, remember it's not times in, it's a composition because there's no brackets, right? There's missing brackets because remember f of x has a bracket. But so it's saying f of. If I then add the brackets in, it'd be f of G inverse of x bracket bracket. So it's the composition. So I'm plugging G inverse of x into f. So it's a composition. But again, you should be quite familiar with that sort of notation. So I'm going to write that down then. So I'm going to say f of G inverse of 1. Okay, so we want the range of that. Okay, so what this is saying is what it's told again. We had to do part C for a reason. It asks us for the G inverse 1 range for a reason. Those are the range of values of G inverse of x. So if I plug any value of G of x into here, there's only a certain amount I can plug into f of x, right? So f of x then, x almost then, x is G inverse of x. You have to be between f of 0 and f of 4, right? Because those are the range of values you can plug in for G inverse. So that's going to be our input. So f has to be between 0 and 4. Hopefully you can see that, right? Because G inverse of 1 again is our input, but our input, as I said, only takes between 0 and 4. So that means has to be between f of 0 and f of 4. And that's what we're going to consider. So then f of 0 is, and then you plug 0 in. So f of 0, I'm just going to write this down. So f of 0 is, actually no, I should show my working, shouldn't I? So I'm going to say f of x is, again, over here, 8x plus 5, was it? Over 2x plus 3? I cannot remember. 8x plus 5 over 2x plus 3, cool. So I'm going to say f of 0 then, if I plug 0 into s, well, it's going to be 5 over 3, right? I don't even need to plug that in, I can see it. And then f of 4 is going to be 8 of 4 plus 5 over 2 of 4 plus 3, which is 37 over 11. Okay, so we've got our endpoints. So then you might be, well, 37 over 11 is greater than 5 over 3. So you might be tempted to then say directly 5 over 3 is between the range of f of g and f of g inverse, right? Between 37 over 11. That actually is right, but you cannot really make that step because what we then need to what we're essentially considering is the range of f of x for all 0 between x and 4. All I've done here is consider the endpoints. What you then need to consider is the function decreasing? And what that means is, say if we have a function here, say between obviously 0 to 4, say, if it's strictly decreasing, then that means actually, well, no, it'd be increasing, wouldn't it? Sorry. So obviously that means is 0 is going to be the minimum value, x is 0, and x is 4 will give the maximum. So obviously as you increase the value of x, the um the curve increases, right? So that's increasing. For God's sake. But what you need to do is kind of get your head around why it's increasing. Most of the time, it's not always, but there's two ways to know it's increasing. One way is algorithmic way. Obviously, you should remember f dash of x has to be greater than 0 for it to be increasing. That's the definition, right? And you can compute the derivative, right, and show that for x, for all x between 0 and 4 or whatever, f dash of x will be positive. If you want to go through that, but it's only 3 marks, you can do that to convince yourself. But then that asks us for part B. Remember, part B, this simplifies to 4 minus 7 over 2x plus 3. Now, between x is 0, I'm going to get rid of all this mess as well here. Now, between x is 0 and 4, which is what our range is, remember, because G inverse has this domain. This denominator will keep getting, if I plug 0 in, you're going to get 3. Right? Because obviously 2 of 0 plus 3 is 3. And then if I plug in 4, 2 of 4 plus 3 would be 11, right? Say. So that means and then as you can see, as 2x plus 3, right? It's like a line; it keeps increasing. So as you add, if you increase the value of x, the denominator gets bigger. Now, if the denominator gets bigger, the fraction, because it's a constant, the fraction will get smaller. Hopefully, you can see that, right? I'm divided by a bigger number, so the fraction will get smaller. But then I'm subtracting by the fraction because it's negative of the fraction. So if a fraction gets smaller, I'm subtracting by a smaller number as x gets bigger. So that means it has to be increasing because it's going to be forced as x gets bigger. I'm minusing a smaller number. So it goes up and up and up as a result. Hopefully you can see that. Because when obviously x is 0, this fraction would be minus 7 over 3. But then when x is 4, it's minus 7 over 11. But then I'm subtracted by a smaller fraction. So, a smaller fraction. So, the overall value would be bigger, right? Hopefully that makes sense, right? Um, so yeah, so as the value of x gets bigger, to reiterate, the denominator gets bigger, so the fraction gets smaller because I'm divided by a bigger number. So then, as x gets bigger, this fraction we're minusing by a smaller number because the overall fraction is smaller. So that means the values of x gets bigger and bigger because we're taking away a smaller number. So therefore, by that logic, without doing any differentiation, if we use part B, we can see the fraction is decreasing. Increasing. Because again, we're taking away by a smaller number as value as x gets bigger. So because it's increasing, that means in the interval 0, it's getting bigger and bigger. As x gets bigger, the function gets bigger. So that means the smallest value of the range is when x is 0, right at the end, at the end point, and then the biggest value would be the other end, which is 4. So because of that, 5 over 3 is the smallest value, and then f of a g inverse gets bigger in between that range, and then at the end it gets the biggest value, 37 over 11. So that is your range. Okay. So you just need to be careful of that. You would actually get that. You don't have in the mark scheme. You don't actually have to justify or give any mention of the fact it's increasing, but you do need to be careful though. You do need to prove to yourself that it is increasing because and multiple things could happen, right? Say if we started at 5 over 3 and then 37 over 11, right? It could look like this, couldn't it? It could be a turning point or a maximum here. And then it wouldn't be just increasing, it increase, then decrease down to 37 over 11, but it's still bigger than the starting point. But that's not the maximum right anymore. but because it's only increasing, there are no turning points. So it's strictly going from A to B, it's strictly going up. So the end points are the minimum and the maximum. Hopefully they made sense. Okay. Um, so with these sort of range questions, you need to basically judge if the function's increasing. Which most of the time it is. For A level, they're not going to make it too tricky. You can kind of assume it is, but again, you just need to confirm it. But you can just jump to the endpoints, right? And then you get this range, and that should be your answer. Yes, so you get a mark for evaluating at each endpoint, right? So you get f of 0 and f of 4, that's for 2 marks, and you get a mark for the range. So that's actually surprising, reference to proving the function's increasing, not proving, but seeing that it's increasing. But you do need, again, like I said, you could have a turning point that actually the maximum. I don't know. I'm not going to get into that, but just be careful with these sort of range questions. But that is the answer. Hopefully, it made sense. Uh, okay, on question 12. We are getting late for time, actually. Um, I'm going to do this very, very quickly then, this question. So f dash. So that's the chain rule. Not the chain rule, the quotient rule. The quotient rule is in the formula book. You do not need to remember it. If we can get it off. Uh, it's here. It's not labeled the quotient rule, but it's there. Okay, so if I copy it, I just reset it, man. So the derivative of f of x over g of x dash, I think it's f dash of x g of x minus g dash of x f of x over g of x all squared, right? F dash of x g of x. Yeah, so that's it. So that's the formula you give it in the formula book. It doesn't say quotient rule, but hopefully you just spot that right. But that's where it is. Now, really, we just substitute. We should spot what f of x and g of x is, right? Well, that's quite not ideal because it says f of x in the question. But uh, um, I'm going to call it a different number then. I'm going to call it. I'm going to. I'll call it h of x. There we are. So then that'd be h dash and then g dash of x h of x. Because purely because I don't want to get mixed up with the f. So I've just called it a different function, call it h. So then h of x is going to be the top one, e to the 3x. G of x is also going to be 4x squared at k. And then we need to compute the derivatives, right? Which is actually not too bad. H dash of x is going to be 3e to the 3x. Hopefully you can see that. And then g dash of x is going to be 8x. And then the k goes away as the constant. Then we just substitute the formula in. So f dash, which is this quotient dash, the first derivative, if we substitute it in, h dash is 3e to the 3x. G of x is 4x squared at k. And then minus g dash, which is 8x. And for h of x, which is e to the 3x. And that's all over 4x squared of k all squared, because that's g of x squared. Then we just need to simplify it. Well, actually, I noticed we could factor out e to the 3x here. So that's going to be e to the 3x of 3 lots of 4x squared of k. Then I could expand this out to then say 12x squared add 3k. So then times it all by 3 there. Factor the e to the 3x and then minus 8x all over 4x squared and k squared. What does it say it wants us to do after this? We need to write it in the form of 12x squared minus 8x plus 3k, lots of another function. Okay, my 12x squared, was it minus 8? Yeah, so that's so we got this bit, this quadratic. So therefore, the derivative will then become, I forgot to say, 12x squared minus 8x is 3k, lots of e to the 3x over 4x squared and k all squared. So that's our function. Cool. And then then it says, I believe, what was it? The range of so have at least one stationary point. Find the range of possible values of k. So at least one stationary point. So remember, we need to consider f dash of x is 0 for a stationary point. That means this whole thing has to be equal to 0. So 12x squared minus 8x plus 3k of e to the 3x all over 4x squared and k all squared has to equal 0. As I said earlier, the numerator has to be 0. If you times across, this all 4x squared plus k squared times 0 is still 0, so that doesn't matter. So then you're just left with e to the 3x of 12x squared minus 8x of 3k is equal to 0. But e to the 3x cannot be 0. Again, look at question 2 when it asks to sketch an exponential graph. E to the x, the asymptote is at 0. So but it can never be 0, right? So e to the x, e to the 3x, no matter what it is, it's never ever 0. Okay, but it's the asymptote, right? So that cannot be 0. So therefore, the only solution to this will come from 12x squared minus 8x of 3k equals 0. Now we are told there is at least one root, one turning point. So there's at least one solution. Well, if we have a quadratic and there's at least one solution, that means that the discriminant is greater than or equal to 0, no? So therefore the discriminant is minus b squared, which is minus 8 squared, minus 4 over 12 of 3k is greater than or equal to 0. And then we just solve for k. So then that would mean 64 minus 1, 2, 3, 48, right? Times 3k is greater than or equal to 0. So that's 64 minus 144k. Right. I've got the maths right there. Yes, 144. So therefore k is greater than... I need to be careful here. Minus 144k is greater than minus 64. Now what I'm going to do is divide by minus 1, but bear in mind the inequality will flip. Because if your times are divided by minus, you have to flip the sign. So 144k is less than or equal to 64, therefore k, if you divide them by 144, you get 64 divided by 144, you get 4 over 9. So that's our solution. But let's check the question one more time. Find the range. You might be fine there, but it says k is a positive constant. So our upper bound is going to be greater than 0, right? A lower bound. So I'm going to say k is positive. So k greater than 0. Therefore 0 is between k. That's equal to 4 over 9. Now I'm going to give it a very important distinction you need to make as well. Positive means it has to be strictly above 0. Because I guess think about it, 0 has no sign, really. It's not negative or positive. So it's not negative or positive. So you have to consider the next number after 0, which should be a positive sign. So it has to be strictly above 0. If you wanted to include grade greater than or equal to 0, we say k is non-negative. Again, that's because it doesn't have a negative sign. So 0 doesn't have a negative sign. but it doesn't have a positive sign either. So that's an important distinction to make that you do have to remember with positivity. But normally they're not that pedantic. But that is the range of values, I believe. Yep. I missed a question as well. Sorry. This one here. It's a simple proof one. So prove using algebra that this is even for all n. They kind of give you a clue here. Even. So what you're going to need to is consider odd n, which is going to look like 2k minus 1, and even n, which is going to be 2k, right? Then you need to substitute that n, and both of these instances you'll be able to factorize into 2 of something, right, which is even, and that will be your proof. Okay, so it's proof by exhaustion now. Just a little comment on that. Okay, we did that bit. Cool. Vectors. Okay, let's go over this. So again, it's fairly typical sort of vectors question as well, really. Okay, so we have relative to a fixed origin. We have position vectors for A, B, and C. I noticed P's there. And it says given A, B, and C is in a straight line, find the value of P. Okay. So you should remember, even from G to C, a straight line means that well, they're all on the line, but that means any vector you can make between A, B, and C are parallel to each other. So what that means is AB would be also equal to some lots of AC. Okay? So because they have the same direction, but obviously not the same magnitude, which is why we have a scale multiple of K. So we can deduce that because it's a straight line. So as A, B, and C are, I'm going to say this fancy word collinear, which means they all lie on the straight line. So then I could just find the vectors, right? So AB, you should know, is OB minus OA. But we know the position vector of B, which is, well, there's no I component, so it's 0, 4, and 6, minus OA, which is 4 minus 3 and 5. And then we can then we can work that out. So 0 minus 4 is, well, just minus 4. 4 minus 3 is 7, and 6 minus 5 is 1. And then to find AC, that's going to be OC minus OA. So the position vector C is minus 16, P, and 10. Okay. Hopefully you recognize this way. We can write this in column vector form. So I, J, and K corresponds to the X, Y, Z, so the top, the middle, and the bottom number. And then minus A here is, again, 4, minus 3, and 5. And that will be minus 16 minus 4 is minus 20. P minus 3 is P add 3. And 10 minus 5 is 5. So then I said this, AB is K lots of AC. So then, if you substitute that in, minus 4, 7, 1 is K lots of minus 20, P at 3, and 5. So then if you compare coefficients, that means minus 4 is minus 20k, which obviously then means k is going to be 5, if you solve for k there. Minus 4 divided by minus 2, no, sorry, k would be a fifth, wouldn't it? My apologies. Minus 4 divided by minus 20 would be 4 over 20, which would be a fifth. Okay, and then compare the second equation with a p. I'm going to write it down here. So then I compare so I'll compare the first component, right? Minus 4 is k lots of minus 20. Then I can do the same for the second component. So 7 will be equal to k, but we know what k is, it's a fifth. of p plus 3. I can times by 5 to get rid of it, so 35 is p had 3. Therefore, p would be 32. Cool. So that's part A. Ask for value p. Cool. So, on question B now. What's going on here? So then the line segment, now it said the line segment O to B is extended to a point D, such that CD is parallel to OA. So again, let's consider this little line we have here, A, B, and C. So what's going on here? I'm going to write that here actually. We have A, B, and C, but we have this point D, so O to B. So say the origin's here, right? O. Then we have a point D on O. So O to B is going to be here. So then O to D is going to be somewhere like here, right? So, but then we said that C to D here is parallel to O to A. And you can kind of see that there, right? This is parallel to OA. We need to find the magnitude of OD. So we need to find OD first and then find the length. Okay. I'm going to write that on the side, I think, actually, because I've got all the vectors here. Okay. So we need to find OD. Well, I'm going to make use of this fact first of all. C to D is parallel to OA, so that's going to be another multiple of OA. I'm going to call this multiple. I'm going to call it. I'm going to be fancy and use lambda. You call it any letter you want, actually. Why am I overthinking this? You can call it n, I guess, if you wanted to. If you're not comfortable with lambda, nah, that doesn't look right. I'm going to call it lambda. There we are. Lambda of OA. So that's just another scalar multiple. But to C to D, remember, that's going to be OD minus OC. That's going to be lambda lots of OA. But so then OD, we want OD. So actually OD is going to be OC at lambda lots of OA. Which is minus 16 p, which is 32, and 10. Add lambda lots of lambda we don't know yet. It's just a scalar multiple of OA, which is 4 minus 3 and 5. And we can bring that together. Hang on. God. Minus 16 add 4 lambda, 32 minus 3 lambda, and 10 add 5 lambda. Okay, but we need to find lambda somehow. So with vectors, then you need to find another way of getting the vector. But here we said OB is extended to a point D. So that means OD lies on OB. Again, with this same argument, like we did in part A, we have O, then B, and then D, right? So O, B, and D lie on the same line. So by that logic as well, O to B is parallel to O to D. So O to D is again going to be some multiple of O to B. Oh God, I'm going to call that. I'm going to call that T, O, B, Tob. So then that's going to be T lots of O to B is given us in the question. The position vector of B is, by the way, O to B, O to A, you should remember it's a position vector of A, B, and C or whatever, which we're told. So the position vector B is 0, 4, and 6. Oh, for God's sake. 0, 4, 6, which is going to be 0 times t 0, and then 4t, and then 6t. Now, those are two ways of getting OD, right? These two must be the same because they're both OD. So I've used the two different conditions they've given us to find two ways of getting OD. The fact D lies on the line OB, and that CD is parallel to OA. Okay. So therefore, the first vector minus 16 add 4 lambda, 32 minus 3 lambda, 10 add 5 lambda has to be 0, 4t, and 6t. And the idea is I want to find t or lambda, because then I can find an actual numerical answer. Well, I can, because then I can say that, but if I compare the first bit, minus 16 add 4 lambda is equal to 0. Therefore, lambda is going to be 16 over 4, which is 4. If I solve for lambda, right? But then I'm good, because I know then that OD is, if I remember, minus 16 at 4 lambda, which is here. That's one way of writing OD. So I can substitute lambda into here. So minus 16 add 4 of 4, 32 minus 3 of 4, and 10 add 5 of 4. Put that into the calculator, you get this answer. Okay. Well, yeah, you get 0 for the first bit. Then you get 32 minus 3 of 4. You get 20. And then 10 add 5 of 4, you get 30. So that's that. So now we've got an actual vector for OD. Therefore, the length of OD is going to be the Pythagoras of the distance of the part. So it's going to be 20 squared, or 0 squared, which is 0, add 20 squared, add 30 squared. And then put that to the calculator, you get 10 root 13. And that should be the answer, I believe. As a simplified surd, yeah, so you can't simplify that anymore. Yeah, 10 root 13, that's the answer. Cool, hopefully that made sense. So with these sort of vector questions, two things with these sort of things. A is that you really need to sketch, right, what's going on. You need to draw a sort of diagram of what's going on. And B, try and find, you're probably going to need multiple ways of getting to a vector. So like we did here with OD, we first use the fact D's on OB, this line here. So OD's a multiple of OB because they're parallel. And then CD parallel to OA, so that's another multiple between them. And then I split up CD in terms of OD minus OC. And then I've got from there. So then what I got eventually was two different vectors for OB, which are the same, so I'm going to equate them together and solve. And then I went from there. Hopefully that made sense. But I know vectors can be a bit tricky. Okay, question 14. Okay, I'm running out of time here, so I'm actually gonna I was gonna go over this, but I'm running out of time. I'm gonna briefly go over it. So for part A here, again, expressive partial fraction is very standard. So 3 over 2x minus 1, x plus 1, that's can be split in the form a of 2x minus 1 plus b over x plus 1. It's a fairly standard partial fraction. Then I can combine and say a of x plus 1 plus b of 2x minus 1 over 2x minus 1, x plus 1. Then I can compare the numerator. So I can say 3 has to be identical to a of x plus 1 plus b of 2x minus 1. Then you just say two values to find a and b, so it's simultaneous equations. You can do that however you want. I just say two letters. So I usually let each bracket equal to 0. So I say x is minus 1. So that means a would cancel to leave with b, and x would then be a half to get rid of the b. and then you solve A and B. And then for question 2, it's a simultaneous equation. So we have dv by dt is 3v over 2t minus 1, t plus 1. Then we need to split it, so we separate the variables. So I'm going to times by dt to the left of dv is 3v over 2t minus 1. T plus 1 dt. That's the first step you want to do. Then I want to get v on this side with the dv, so I'm going to divide by 1 over v. Not times by 1 over it, we'll divide by v. So 1 over v dv is then 3 over 2t minus 1, t plus 1 dt. And because the dv's on each, all the v's on one side of dt's on the other, I can then integrate. So 1 over v dv is 3 lots of the integral of 1 over 2t minus 1, t plus 1 dt. Then I would reintroduce the partial fractions, because then every single we can get we can get like a fraction that looks like this, right? A over x plus 1 plus b over 2x plus minus 1 or whatever. But then this you should realise that a fraction like this integrates to the form of ln mod v, okay? And then I go from there, I use log rules to then find the missing values and go on from there. Okay, so ln v is going to be logs of this as well. But I wanted to touch a bit on part C. So once you solve that, you get v's this, okay? I'm going to leave that to you there, but it shouldn't be too tricky to work out. Okay, so part C then, it's talking about there is a time delay between the chemicals being mixed and oxygen being produced, and there's a limit to the total volume of oxygen produced. So the time delay, the chemicals being mixed and produced, and oxygen being produced. So the time delay between chemicals being mixed and oxygen being produced, that means essentially, for God's sake, that essentially, if I don't know, it looks a bit like this. The curve will be flat and nothing will happen for the first few seconds, and then the effect takes place. So there's this sort of delay. The way to work that out is consider when t is 0. And then v would be 3 of minus 1 over 1. Hang on, that's not right. Hang on, why is that negative? You would get minus 3. No, because you're not saying t0. My apologies. Yeah, t0. Yeah, obviously there's still delay. You want to find the final value of t such that v, initially there's no volume, right, of oxygen produced. That's what v represents. So you want v0, and then you want to find the value of t that gives. So like I said, if you're solving a fraction, so that means the numerator has to be equal to 0. So 3 over 2t minus 1 equals 0. Therefore, 2t minus 1 equals 0. So t would be a half. Now, t's in hours, so you want half of an hour, which is 30 minutes. So that makes sense, right? So there's a 30-minute delay between then when v starts increasing. So v's 0 for 30 minutes, okay? And because it looks like this sort of graph here. So v's 0 here at this point, then it obviously goes up after the 30 minutes, okay? So hopefully that made sense. And then for part B, the limit. So it says the limit to the total volume produced. And that means as the time goes on and on, as t gets infinity, as t gets very large, t goes to infinity, v has to tend to some sort of number, right? It's a limit to the volume. So we need to find what happens to this function as t goes to infinity. Now, I'm not really happy with these sort of questions in the A level because they don't teach you this. in any textbooks. It's quite a niche knowledge you need to know. The only way you could kind of perhaps, well, there is a way with A level with limits like this. You want to find when t goes to infinity, plug in big, massively big numbers for t in the function, and then you'll get a number for v. It will go towards a clear number. So for example, so if I did that approach, if I substitute t as a million into v, for example, so 3 are 2 times a million minus 1 over million add 1. I get 5.9991. That's obviously going towards 6. So my instinct is to say the limit is 6. That's one way you can work it out. At least at A level, the V will tend to 6. So the limit to the oxygen is 6. And it's in meters cubed. The way to formalize this, however, without a calculator, without testing the values as t goes to infinity, so the limit, well, I'm going to expand this out. So I'm going to say it's 6t minus 1 over t plus 1. What I'm then going to do is actually divide by t. So this is 6 minus 1 over t over 1 plus 1 over t. Hopefully you realise that. I times top and bottom by 1 over t. Then notice when t goes to infinity, 1 over t goes to 0. And again, you can't spot that with like the reciprocal graph. It will look a bit like this. And again, you can try that with large values. Put in big values in the denominator. You essentially go to 0, right? You'll spot that. And it's like with the graph 1 over x, reciprocal graph. With that in mind, hopefully you realise that limit. Then as t goes to infinity, the 1 over t's go to 0. So it becomes 6 minus 0 over 1 plus 0, which is 6. So that the formal then, the limit formally 6. So there's two ways of working it out, but they don't go over that in the textbook or anything. So I don't know about that Edexcel. I don't know. But that's how you can work out the limit with these sort of things, okay? Okay, can't be more left, surely. Oh, was that question 14 I did? It was, okay. So yeah, that's the general gist of that sort of thing. 15 and 16, I'll do more properly. Okay, so given that the first 3 terms of a geometric series is these 3, show this. Okay, so the general technique is to realise what you're going to divide some stuff. Let me go over this. So, if it's a geometric series, the first 3 terms, well, the geometric series sequence goes AR squared, AR cubed, da, 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 da. So you start with initial value A, and then you times by R every time, right? So you times by R for each term. So with that in mind, why is it not rubbing out? There we are. This is going to be A, the first term, then this is going to be AR, then that's going to be AR squared. Are you okay? Cool. So then, I can actually say AR divide, if I divide the second term by the first, that is AR over A, which is R. And then the second term is 5 plus 2 sine theta over 12 cos theta. In the same way, AR squared, then if I divide the third term by the second, then I'm going to say AR squared divided by AR. Again, that's going to be R. But this time, the third term divided by the second is 6 tan theta over 5 plus 2 sine theta. Harder than GCSE, yeah. Yeah, I hope you're ready for Wednesday, hopefully. So we're A level and GCSE at the exact same time for their maths exams. They're both on the Wednesday. but they're both the same, right? So r has to be the same. So we can equate them to then say 5 plus 2 sine theta over 12 cos theta. That's going to be equal to 6 tan theta over 5 plus 2 sine theta. And then we need to do some stuff with this, right, to get the equation they want. So then we can cross multiply, I guess, to say 5 plus 2 sine theta all squared, because we timed it by itself. That's going to be 12 cos theta tan theta. Now, I remember if I go back, I forgot to say, there's a sine squared term. So I think it's going to be wise to expand this bracket, right? And in general, you want to expand brackets anyway. So if I expand that, it's going to be 4 sine squared theta, and then 2 theta sine theta times 5 is 10 times 2, that would be 20 sine theta, at 25, and that's going to be 12 cos tan theta. As long as I pass it, be happy. I'm too stupid to do A-level math. Aw. But my friend doing A-level maths and further maths. Oh, if he's sitting, and good luck to him as well. But yeah, all you really need these days is fours, really. I wouldn't stress too much about it. It's a bit messy here. Cos theta, tan theta. So I've done really much I can do here. But I noticed there's a cos theta, tan theta, and this identity staring at me. Tan theta, you should remember, is sine theta over cos theta. So that means this, because this right hand side is going to be 12 cos theta times by sine over cos, right? Now what I notice is the cos will cancel, so then I'm left with 12 sine theta. So therefore, for sine squared theta add 20 sine theta add 25 is going to be 12 sine theta. And then I can move it to one side. Better than writing. Yeah, I'm the opposite. I couldn't stand English when I was doing my GCSEs. Yeah, I'm going to read the sine theta then. So then say 4 sine squared theta. Then 20 minus 12 is going to be plus 8 sine theta. 25 is 0, and it should be the equation I wanted, right? Minus 52. Oh dear, what happened here? 5 plus 2, 6. Okay, interesting. Oh, I might have expanded it wrong, perhaps. Uh, 20. Interesting. Any style you might. No, so, I've done all the A-level stuff before. I've actually not done maths in years. But I'm quite good at it. I did get an A star in the end in the A level, but I'm coming back now to help people essentially. But I'm still a bit rusty. But yeah, it's a long way away. But yeah, I did get an A star in the A level in the end. Okay, but where did the 52 come from? Let's have a look. Oh, that's why, because I didn't times the 12 by the 6. So 12 times 6 is going to be 72. There we are. I forgot to do that. Cool. So that's going to be 72 cos theta tan theta. So then that'll be 72. 72. And then I'm minusing 20 minus 72 will get me minus 52, which is what they wanted. There we go. Cool. Probably getting there. So yeah, if I did that A-level English though, I'd probably get like a U. So we all have our strengths. So yeah, so we've got part A in the end. Okay, then it says theta is obtuse. So that's giving us that into our range of values for theta. So if it's obtuse, it's going to be above pi over 2, which is 90, and between pi, right, 180. Because anything above 180 is going to be a reflex angle, right? So that's our range we've got to work in. So we essentially got to solve the equation um, um, to get theta. So I'm going to note that here. Pi over 2 between theta and pi, as theta is obtuse. So I'm going to solve this. So this is very clearly a quadratic. So if I say let u is sine theta, then this becomes 4u squared minus 52u at 25 is 0. Now I think we can solve this, can't we? And that will become u is 25 over 2, or u is a half. And then I'll substitute u back in. That means sine theta is 25 over 2, or sine theta is a half. Now 25 over 2, you can do that on the you can try that on the calculator, but it has no solution because 25 over 2, where is it? Is above 1. And remember the sine graph only goes up to 1. So that you'll have no solution here. So our only solution will come from sine theta is a half. So then theta, if we arc sine it, arc sine of a half will be, well, it's in degrees now, 30, which is pi over 6. I've been meeting about my A-level options. I really can't be asked anymore. I've been doing these meetings for about 3 weeks now. It's gone on for a while, the 3 weeks. I think it's sort of A levels as well. You really need to be certain kind of what you want to do because A levels are not easy, and I think a lot of people tell you that. So I think they're just having your best interest, even though it feels like a drag. So yes, pi for 6, but which is about 30, but 30 is not it's not obtuse, so we need to find another solution. But how are we going to get the other solution? Well, let's consider a sine graph, right? So if we have 30 about pi over 6, right? Which is when it's a half. The next solution is going to be when you take pi away from pi over 6. Because I noticed the distance between 0 and pi over 6 here is the same distance between pi and this intersection here. So the next solution is going to be pi minus pi over 6 is going to be 5 pi over 6. And that is between 90 pi over 2 and pi, or 90 and 180. So it's obtuse, which is what we want. So as theta is obtuse, theta must be 5 pi over 6. And I'll echo again, like I said earlier, if you are unsure about any solutions you solved like this, put the angle back into the sine. So sine of 5 pi over 6. And you should get back up. Oh, it's in degrees again, that's why. Sine, you get a half, so we get what we want. So that is indeed a solution. So that's the value of theta then. Cool. So let's have a look at part C. For 5 marks, show that sum of infinity is given in the form here. Okay. I picked history, philosophy, and Spanish. I'm the only one to pick Spanish, so my Spanish speaks who run the course for me. Have less lessons a week. Some lessons through the year 13. Doing Russian GCSE next year. I'll be taking that to AS level, which will take a lot of study time. Wow. I've got to say, hats off anyone to languages, man. They're really, really tough. But would say at A level, not a lot of people do languages, so it kind of does make sense that you'd probably be not the only one there. But yeah, but I guess you could see it as one-to-one tuition in a way, so maybe it might be better. I don't know, but yeah. Um, I wouldn't stress too much about the AS level. It's just the A2 that counts at the end. You know, at the end of year 13. Um, but yeah, I hope you enjoy it. Okay, so we need it's asked about the sum to infinity. So when we have sum to infinity, we need to consider the first term, which is A. Remember that's going to be 12 cos theta. Remember here. Um, that's 12 cos theta. Um, and we need a common ratio. Now, common ratio, for examples here. So 5 plus, I'm going to leave some space here actually. Then R is 5 plus 2 sine theta over 12 cos theta. Okay. Well, we know that theta is 5 pi over 6. We solved that in part B. So therefore, if I plug 5 pi over 6 into these values, 12 cos of 5 pi over 6 is going to be minus 6 root 3. And R then is going to be 5 plus 2 sine of 5 pi over 6. And then 12 cos theta is going to be 12 of cos of 5 pi over 6. And the ratio would be minus root 3 over 3. Thanks, to be honest, been studying more Russian rather than the subject doing this year. Whilst revising physics paper 1, learnt some Russian. Nice, nice. Uh, yeah, I know it's tempting. Revise subjects you like the most. I get that. So we found A and R. So then our sum to infinity, which is S infinity, is A over 1 minus R. And that is in the formula book. But I'm not going to get the formula book out because it's going to reset my page for some reason. But that is the expression, 1 minus R. Now I'm going to just substitute this in. So A is minus 6 root 3. And 1 minus R is going to be 1 minus root 3 over 3. So then that's a minus 6 root 3. And then I'm going to simplify the bottom bit. So it's going to be then 1 minus is adding. 1 add root 3 over 3. Okay. Okay, let's get rid of this bit here. Then I'm going to make this as one fraction so I can clearly see what's going on. So it's going to be minus 6 root 3. Then I'm going to 1 add root 3 over 3. Well, that's going to be 3 add root 3, right, for times 3 here. To then get a fact denominator of 3. Well, then you can visualize it like this. So then you can say minus 6 root 3 if you're struggling with this sort of thing. This is same as dividing by the fraction 3 plus root 3 over 3. Okay? And then if you remember keep flip change, KFC from G to C, that's minus 6 root 3 times the reciprocal. So it's going to be 3 over 3 plus root 3, and then that would be minus 18 root 3 over 3 plus root 3. And from there, it's just rationalising the denominator. Okay. I meant how a car engine works by learning Macbeth quotes. I procrastinate a lot. uh, yeah, I hope the exams went well so far, though. I think you had the English literature now, haven't you? Okay, let's get rid of more space here. And then I'm going to rationalise it. So it's going to need to look like 3 minus root 3 over 3 minus root 3. Because it's a difference of 2 squared. Because then the denominator will go to 9 minus 3, which would be 6. And then we can expand this. So 3 times minus 18 root 3 is going to be minus minus 54 root 3. Oh god, what's going on here? And then minus root 3 times minus 18 root 3 is going to be plus 18 lots of 3. Okay, and that will go to minus 50. Oh, yeah, 54. So that would be plus 54. And then I've noticed I can factor 54 out. So 54 over 6 of 1 minus root 3. Okay, so 1 here, and then the minus root 3 there. And 54 over 6, I believe, should simplify, right? 54 divided by 6 is 9. So that'll go to 9, lots of 1 minus root 3. And I don't think you can do any more with that. Let me check the answer. What's it asking? Give it in the form k of 1 minus root 3, which is exactly what it got, right? So k would be 9. Cool. And now it is 5 marks, so I don't think you'd get the marks just for putting it into the calculator, and just because obviously the calculator will simplify it for you. But I don't think it would actually give you this. I think you have to do it yourself. But that's how you do it. Yeah, we finished English Lit and Religious Studies. Well, I finished those other ones. I've finished as well, but I don't know what they are. Oh, okay, cool. Yeah, it's nice when you get towards the end though. You start crossing the exams you finished off, so you have left. You haven't got much left. Okay, we're on the final question now. It's a nasty parametric one. So we are given this figure here with a parametric equation: x is 2 tan t plus 1 y is 2 sec squared, add 3. The line L, which is drawn up here as well, is normal to the curve at this point P when t is pi 4. So we need to find an equation for L via parametric differentiation. By differentiation, obviously it's going to do with gradients. Okay, cool. This week, history and English lang finish as well. I'm excited. Nice. We're going to do these for GC paper 3. Yes, that is the plan. I did some on the weekend. I'm going to do probably another little session tomorrow. But the awkward thing is, like I said, the A level and the GC exam is both on Wednesday. So I've got to balance both of them on Tuesday tomorrow. So I'm going to do a bit of GC for paper 2 tomorrow, and then math A level. But for paper 3, yes. So once I then see what's on paper 2, then I can kind of do some more like cross-referencing to then come up with like better revision for paper 3. But that is the aim, yes. Okay. So part A, use parametric differentiation. So to find a gradient, obviously that's going to be dy by dx. So let's say dy dx. So our gradient is dy dx, but it is parametric. So this is the same as saying dy over dt over dx dt. And you can kind of think about it because the dt's will cancel out, right? So you just be simplified to dy dx. So that's the way of thinking about it. Parametrics. Parametrics actually make a lot of sense, really, once you realise you can kind of do stuff like that. But yeah, so what we got left then is just work out dy dt and dx dt. So let me copy the equation down. X is 2 tan t plus 1 and y would be nice. To be honest, you're going through this better than my teachers. Some of this makes kind of sense. No, that's nice to say. Thanks. Then y is yeah. When I do longer on this, my laptop starts to freeze a little bit. Y 2 sec squared t at 3. Okay. Uh, Cool. So I need dy by dt first of all. So I need to differentiate sec squared. The way I'm going to do that, well, I'm going to realise that I can say this is 2 of sec squared, sec t all squared. Oh, God damn it. All squared plus 3. Are you going to bed now? Yeah, it's getting a bit late to be fair. Good luck with this. See you pay 3. Nice. Thank you. Hope you get good rest as well. See ya. And yeah, so we write it like this. Why? Because this is going to be a chain rule. Because then dy dt, well, again, you keep the constant at the 2. Then I differentiate what's inside the 2, and then I times by the power. Because remember, differentiation, you times by the power, and then you knock one off. So 2 to the factor the 2 out, then 2 times the power. Then I differentiate inside the what's inside the bracket, right? So sec of t. Now, actually, it's given in the formula book that uh, differential sec of t is it's in the differential section, differentiation section. If I can find it, that's the integration section. Here, the differentiation. So sec x here will differentiate. Now k is 1, so sec x is sec x tan x. Okay. Now that you just given. I'm gonna have to scroll down. Oh, nice. Okay. So that is sec t. If it lets me write. There we go. Sec t tan t. So then the differential in the bracket to differentiation of sec t is going to be sec t tan t. Loads of t's here. Oh god. Then I knock one off the bracket, so it's going to be sec t of 2 minus 1, which is just 1. So I'm just times it by another sec t. Okay, that's the chain rule. Really, the examiners do expect you to be able to do that by not by memory, sorry, chain rule stuff like that without having to like do extra stuff. So you could say u is sec t, and then say what dy by du, no dy by dt, dy by du times by du by dt. But you just kind of need to do it all in one go, really. So that'll be 4 sec squared t tan t. Okay. Now, x squared. Not squared. Sorry, dx by dt. So that's 2 lots of differential tan plus 1, and also said the plus 3 goes away because it's a constant. So the differential tan, that's going to be sec squared. So it's going to be 2 sec squared t. That's something you have to recognise. Actually, no, you don't have to recognise. Sorry, it gives you in the formula book. I just said yes. Tan x here goes to sec squared x. So again, that's in the formula book, and that's it, right? Therefore, if we combine these together, I then get dy by dt is going to be dy dx, sorry, the overall derivative, which determines our gradient. That will be dy by dt, so that's 4 sec squared t tan t over dx by dt. So that would be 2 sec squared t. Now the sec squares cancel, and the 4 and the 2 cancel to be left with 2 tan t. So that's our gradient for t. Now it says at p, remember the gradient at P, T was pi over 4. So the gradient, I'll go back and you can see. So T is pi over 4 at P, there. Right. So I'm substituting T is pi over 4 into the gradient. So the gradient's going to be 2 tan of pi over 4, which should just be 2, I believe. Let me double check that there. Which is 2, cool. So that's our gradient, that's m. So remember now the equation of the line is going to look like 2x plus c. But actually it's asking for the normal. So actually, the normal, so that's the tangent gradient, right? That's the gradient of the tangent at that point. The normal at that point is going to be the negative reciprocal. It's going to be 9.5 because they're perpendicular, the normal and the tangent. So therefore, y is going to be -1/2 x add c. Now, we need to find c. How are we going to do that? Well, we know the point. We know t is pi over 4. So therefore, x is at t of pi over 4. Remember, x is 2 tan t, was it? Add something. 2 tan t add 1. There we are. So it's going to be 2 tan of pi over 4 add 1, which should be 3. And y was 2 sec squared of pi over 4 add 3, was it? I can't remember what it was. Yeah, 2 sec squared t add 3. Cool. And then you put that into the calculator. That's going to be 2 sec. That's going to be 2, which is 1 over cos, because obviously sec is 1 over cos of pi over 4 all squared. Add 3, which will get you 7. So that means P is the 0.37. So if we sub P into the line, we will get 7 is -1/2 of 3 add C, which means C is 7 add 3 over 2, which is 17 over 2. So therefore, the equation of the normal at P is going to be y is -1/2 x add 17 over 2. And hopefully that should be what they got. Yes, -1/2 x is 17 over 2. Cool. Then it says for part B, show that all points on C satisfy this equation here. So again, this is quite a common exam thing, right? They ask you the parametric and ask you to show this equation, right, that between y and x to get rid of the t's. The best strategy, in my opinion, is to substitute the x in, and when you sub x into all of this, you get y at the end. So I'm going to do that. So I'm going to say 1/2 of x minus 1 squared, add 5. That's going to be 1/2 of 2 tan t, add 1. Oh, the t's are really looking like add pluses and ones here. Try and make it a bit more clearer. Add 1. There we are. -1. Squared, add 5. So that'd be 1/2 of 2 tan t squared plus 5, because the 1 minus 1 cancel. So then that's going to be 1/2, well, 4 tan squared t, add 1/2, that's going to be 2 tan squared t, add 5. But why sec squared? But we know an expression between tan squared and sec squared. You should know 1 plus tan squared t is sec squared t for any angle, right? So that means if I substitute tan squared in, that's going to be 2 lots of sec squared t minus 1, add 5. That's going to be 2 sec squared t minus 2, add 5, which is going to be 2 sec squared t, add 3. And that is equal to y. So we've shown it. And that is the best strategy. Do not really, under any circumstance, try and rearrange one of them to get t on its own and then plug t into the other. It's a mess. You're going to get arctan, arcsine, arccos. It's going to be a whole mess. Don't go down that route. That's normally that you don't want to go down that route normally. What you want to do instead, normally they give you an equation that you need to show. Just substitute x in and do all that and then get y at the end. That's good. Yeah, and then we are on the last question now, and it's a really, really nasty question. But I've actually seen this in 2018. I did that sort of a very similar sort of question. But I will say this is a little bit more structured than 2018, so it's slightly easier. But the bulk of the questions are the same, and it is very, very nasty. Oh, I was there for ages, man, doing this in this when I did 2018. But now I know how to approach it. So, what's going on? Let me read the question actually. Let's scroll down. So we have this equation, cool. Then we have another straight line with equation y is minus a half x of k. I immediately spot the relationship between the normal because they have the same gradient, right? So this line intersects C at 2 distinct points. Find the range of values of k. Right. So what's going on here is if we have our normal. Remember, our normal is y is minus a half x add 17 over 2. What we want to find is the general line, y is minus half x add k. Now, if we add in a number at the end, it's kind of like saying f of x add k, right? F of x is minus a half x. If you're adding k, you're basically shifting the line up or down by k units. So this line is essentially just getting shifted up or down, right? But the gradient remains the same. That's all we're allowed to do essentially is move the line up and down. So what we need to do, if I get rid of it now, is when we shift the line, I would get the ruler out, but it's going to be a whole mess. I know it's going to be an absolute mess. I do have a ruler tool on here, but it's just going to be an absolute mess. So I try to do best I can with my drawing. So you got to imagine you did place a ruler at L, the line L here. Then you can only shift it up or down. Where is the value? Where is that line going to cross the curve twice? If I imagine the line over here, I keep going down. The first point is going to be the first point where the line crosses the curve here. It's going to be here, right? And it's going to intersect somewhere there. That's the first point of the line. If I shift it down, where it will have two intersections, right? So it's going to be where the line, this minus half x plus k, is where it's going to cross. Hang on. This end point of the curve. So the smallest value of x here. So what we need to do is essentially find the smallest value of x, substitute, and then the value of y, and then we can find k by substituting x and y into it. So I'm probably going to do that here actually. So what is our minimum value of x? So you're probably going to be thinking t minus pi over 4. That would give the smallest value, and you're right. But why is that? Because again, think about a tan graph. Remember, it's 2 tan t, so it's going to be some lots of tan. A tan graph looks like this, right? Obviously between obviously asymptotes. But between minus pi over 4, which is here, and pi over 3, which is about there, is obviously increasing. So the smallest value of t would give the smallest value of x, right? because tan x will be smallest in this range of t at minus pi over 4. So the smallest value of x is when t is minus pi over 4. So we need to substitute t is minus pi over 4 to find this point I've circled at the end, if this laptop will allow me to. So t is minus pi over 4. So this point here I've circled, right? The end point, right? Actually, I'll clarify it a bit more. There, right? Let me get rid of some of these lines here. So that end point, yes? That's what we're finding. So then the x will be the smallest value of x again at minus pi over 4. That's 2 tan of minus pi over 4. Add 1. I'm just going to put that into calculator. I'm not going to show the substitution. Just to make more room. So 2 tan of minus pi over 4. So that's going to be minus 2 add 1. That's going to be minus 1. And y would be, and then at minus pi over 4, y would be 2 sec squared. So that's 2 1 over cos of minus pi over 4. And that's all squared. Add 3. So that would be 7. And again, that makes sense because obviously P, Y was 7 as well. So they're on the same level. So, okay, that's cool. But then to find the value of K, then I'm going to substitute it into here. Therefore, 7 is going to be minus the half of minus 1. Add K. Therefore, K is 7. So that's going to be minus a half, right? Which is going to be 13 over 2. If I solve that equation. Now, that's one value of K. So what's going to happen then? So as I shift the curve down from, what was it, 17 over 2, this L. If I shift it down, then I get the first intersect. Then I get the where it intersects twice, right? That's cool. So say it's here. I'm gonna make that clearer. Say it's there, very squiggly, but you get the point. Y would be minus a half x, add 13 over 2. That's where it crosses twice. If I go anything above that, as you see, then, like with L, the line will only cross the curve once, and that's not what we want. We need 2 distinct points. What happens if we shift the line down even more? It's going to then keep intersecting twice, isn't it? But then it's going to reach a point eventually. Oh, for God's sake. So it's going to reach a point eventually. So say here, that's cool. But then it's going to reach this light point here. No, that's not the best representation. So it's going to reach a point where, oh, for God's sake, I do apologise. It's freezing out on me. I think what I might start doing is splitting this up in multiple documents, just for it to stop the freezing. So what's going to happen eventually? The curve is only going to hit the curve once at this point here, and then once we go down any further, it's not going to intersect it at all. So what's happening is it's gone from a point where it intersects twice, and then you go down and it intersects once, then it doesn't intersect at all. That is going to be the discriminant, right, between the line and the curve. So what we need to find is the value of K where it intersects once, and then we need to make K above that, okay? So then you shift the curve up to ensure then it has 2 solutions. So what we're going to do, and we know the Cartesian equation, don't we? Because it's a quadratic. I say discriminant because we know the curve equation has this form, and that's a quadratic. So what I'm going to say is, then a half of x minus 1 squared plus 5. That's going to be equal to minus a half x add k. Okay, then I'm going to solve formulate that as a quadratic. So that's going to be a half x squared minus 2x, that'd be minus x, I believe. Minus 2x minus a half, add a half, I'm going to do that over here, actually. It's starting to be a bit messy. I'm going to do it on the right-hand side. Oh, for God's sake, man, it's so slow. Okay, so I'm going to do the equating here. So it's, what is it? Minus a half. No, it was a half, wasn't it? Yeah, it's here. A half of x minus 1 squared at 5. So the y values are equal, so y would be minus a half x at k. Then I need to get rid of this minus sign. There we go. Then expand it, so that would be a half x squared minus x, add a half, add 5, add a half x minus k equals 0. So then that'd be a half x squared minus x plus a half x, that's minus a half x. Add a half, add 5 minus k. That's going to be 11 over 2 minus k equals 0. So then we need the point where it's one root, because anything above that will be will then be two roots. So the discriminant would be, I'm going to get rid of this bit now as well to make more room. Well, actually, it's two distinct points, so I guess it would be greater than equal to greater than 0, right? So the discriminant would be a half minus a half squared minus 4 of a half 11 over 2 minus k greater than 0. For that'd be a quarter minus 4 of a half 11 over 2. That'd be minus 11. Add 2k equals 0. Therefore, k, if I solve that, that's going to be a quarter minus 11. 2k divided by 2, 43 over 8. So that's your solution you solve for k. So that's telling you when the line then first crosses the curve twice, remember here, there's no solution. Say again, I'm going to get rid of all this again. So say originally a line is here, obviously no solutions. Then we shift it up. Then eventually it's going to reach the curve. It's going to touch the curve once here. Then if we shift it up any higher, then it will have two distinct solutions until we shift it to the point where we reach the end point here. And then anything above that will be only one solution, which is obviously like P. So this is your lower bound, because this is corresponds to this point here, where anything above that will ensure k, any value of k above that will have two distinct solutions to the curve. And then when it gets above this, and then when it stops, and then when it goes above this intersection with the furthest point on the curve, then it only becomes one solution. Again, because if I go above then that line, obviously then you see it only intersects the curve on the right hand side once. So the last time it has two intersections is at this point here, which is when k is equal to 13 over 2. So that should be your range of solutions for K. Okay. And I'm just going to check that's right. But that should be the reasoning, right? Just need to probably. I feel I got the numbers wrong here. And let me check. 43/8 less than K less than equal to 13/2. Cool. That is the answer. There we are. That is a very, very, very nasty question. But they do help you out a little bit though by giving you the curve, right? The line, sorry, and then you just need to shift the line down or up and see where that line will then cross the curve twice. Now you do use a discriminant, but what the discriminant will give you here, and you can't just use a discriminant because that only tells because obviously this is a quadratic, right? But the quadratic's cut off here. But then if we use but then if we extend it, what this discriminant does is it works for all values of x, right? If we assumed x was the whole line, which is where we extend this quadratic, that only is when k is greater than 43/8, we assume it's for the whole quadratic. For God's sake, if it lets me draw. Yeah, so we assume for the whole quadratic. So if k was 43/8 or higher, for God's sake, there we go. Obviously, then it would intersect. Obviously, it intersect here, and then it would intersect here. But then the discriminant assumed it would then cross here at this point and this point, and they will always have two distinct solutions. But because we cut off part of the curve, we can't just use a quadratic because we need an upper bound as well. We need an upper limit to compensate for the fact that once the line, sorry, this line y minus y x plus k, once that then reaches the final point on the left, there's no second solution. It will only cross the right side of the curve because we cut off the left side. So we need to find an upper bound as well, which is where we get by then seeing where the curve will then last cross the curve, which is 13/2. Hopefully that made sense, right? It's a very, very nasty question though. But I am going to leave that there because it is getting late for me as well. But hopefully that made sense. I will be uploading this onto YouTube. Yeah, I am going to leave that there then. But I would say anyone as well. Tomorrow I'll be doing another revision session for maths and GCSE and A level. What the plan is to pick the most common, the most prevalent questions that I see on all the past papers, with pretty much every single past paper, and then go over that. So yeah, I'm going to leave that there then. So yeah, that's it for today.